In this video, we continue our discussion of infinite series, and we look at a second example of the limit comparison test. Example 2. Use the limit comparison test to determine whether the following series converges or diverges. Here we have the series 1 to infinity of 1 over the square root of n times n plus 1 times n plus 2. We begin by writing down our series a sub n. That is, n equals 1 to infinity of 1 over the square root of n times n plus 1 times n plus 2. We're going to compare this series to a new series b sub n. So what should we choose b sub n to be? Well, to decipher what b sub n is, usually I take my a sub n series and I look at it a little more deeply. Let me actually multiply out that polynomial that's underneath the radical in the denominator. If I take n and multiply it times n plus 1, I'm just going to do this one time visually to show you what I'm talking about. And then I continue to multiply using distributive property or FOIL, I would get underneath the radical that I had n to the third power plus 2n squared plus another n squared plus 2n. What I'm specifically interested in is the highest degree. That is what I want to do. I want to take the highest degree in the numerator and the highest degree in the denominator and choose that to be my b sub n series. That is, I want to select b sub n to be 1 over the square root of n cubed. Now, I didn't necessarily have to multiply this whole bottom out. I just wanted to do it the first time. I could have also looked here and noticed that when I went to multiply, I would have an n times an n, which give me an n squared, and the n squared times another n, which would have given me n cubed. And again, I'm always looking for the highest degree, so I could have just focused on that aspect and then chosen my b sub n straight from there. So now, in the limit comparison test, we have our a sub n, we have our b sub n, both of which are positive term series, and we're going to apply the limit as n goes to infinity of the quotient of the nth term for each series. In other words, we're going to take the nth term for a sub n, which is 1 over the square root of n times n plus 1 times n plus 2, and divide it by 1 over the square root of n cubed. And we're going to take a limit. So let's take our limit as n goes to infinity. Recall, we have the complex fraction that we're going to put into a more simple fraction by multiplying by the reciprocal of the denominator. And so that means I'm actually just looking at the limit as n goes to infinity of the square root of n cubed over the square root of n times n plus 1 times n plus 2. Now again, for visual purposes, I want to write this out because I already multiplied out my denominator. For visual purposes, let me multiply out and show you that what that's resulting to is underneath, I actually have n cubed plus 3n squared plus 2n, right? Now, the limit as n goes to infinity, as we go to infinity, only the highest degree terms on both the numerator and denominator really have the effect that I'm looking for. So I'm going to be taking the limit as n goes to infinity of the square root of n cubed over the square root of n cubed. And this is just the limit as n goes to infinity of 1, and that's just equal to 1. And what is 1? Well, 1 is a finite number, not equal to 0, and so that means I'm in the first case of the limit comparison test. Now, what did that limit comparison test tell us? That limit comparison test told us that if we resulted in a finite limit not equal to 0, then whatever our b sub n series does, our a sub n series also does. Well, I got so excited about taking a limit, I actually didn't discover or talk about what our b sub n series does. So we can't quite make a conclusion about a sub n yet until we first decipher what b sub n does. So what does b sub n do? Well, what is this series? This series is actually just a p series, isn't it? The square root of n cubed can be rewritten as 1 over n to the 3/2 power. This is a p series, and my power p is 3/2. 3/2 in relationship to 1 is larger than 1, and therefore when I have a p series with a power bigger than 1, my series does what? It converges. Oh, and so the limit comparison test tells us that whatever b sub n does, namely converge, a sub n must also do. That means a sub n also converges. So let me summarize what we discovered. So let the series b sub n equal the series 1 over n to the 3/2 power, or the square root of n cubed. This is a p series that converges. Since the limit as n goes to infinity of a sub n, which is 1 over the square root of n times n plus 1 times n plus 2, divided by 1 over the square root of n cubed, equaled a value 1, which was finite and not equal to 0, the limit comparison test tells us that whatever the first series did, namely b sub n, the second series, a sub n, must also do, our original series. So the limit comparison test tells us that since b sub n converged, our original series, n equals 1 to infinity, of 1 over the square root of n times n plus 1 times n plus 2, also converges.